This Explain Everything video is intended as an instructional resource to help teachers to more effectively conduct the lesson as described in the teacher notes in this unit. The same acceptable use policy restrictions apply to this video as they do to the rest of the curricular materials made available by AMTA. To study this equilibrium system, we will allow solutions of iron 3 nitrate and potassium thiocyanate to react. About 50 milliliters of potassium thiocyanate are added to a beaker. Then a few drops of the iron 3 nitrate are added. Upon addition, the solution turns reddish-orange. Note that no precipitate is formed. Instead, the color is due to the formation of the FeSCN2 positive complex ion. To demonstrate that the color is not due to a reaction between the potassium and nitrate ions, solid potassium nitrate is added to a beaker of water. When stirred, the solution remains colorless. The solution containing FeSCN2 positive ions is split into 5 samples. The one on the left will serve as a control while we experiment with the others. First, we need to provide evidence that an equilibrium system exists and that we didn't just run out of one of the reactants. Suppose the reaction had consumed all the thiocyanate ions in solution. There would be a surplus of iron 3 ions, so adding more of it should not produce any more of the colored FeSCN2 positive. To test this hypothesis, we add another couple drops of iron 3 nitrate to the second tube. We see that the color of the solution darkens, indicating that more of the product was formed, and there must have been some thiocyanate ion present. Perhaps instead all of the iron 3 ions had been consumed. If this is the case, then adding more thiocyanate ions to the tube would not make a difference. To test this hypothesis, we add a few crystals of potassium thiocyanate to the third tube. If all the iron 3 ions had been consumed, then the color should not darken. Instead, we see that more FeSCN2 positive forms, indicating that some iron 3 ions must have been present in solution. In this step, we will try something different. Instead of increasing the concentration of one of the reactants, we will add something that will decrease the concentration of iron 3 ions. Hydroxide ions form a precipitate with iron 3, thus reducing its concentration in solution. When a solution of sodium hydroxide is added, the color lightens, indicating that the concentration of FeSCN2 positive has been reduced. We conclude that the reverse reaction continues at the same rate, but the rate of the forward reaction is reduced. The concentration of FeSCN2 positive decreases until equilibrium is reestablished. In the second test tube, the concentration of the iron 3 ion was increased. This increased the rate of the forward reaction, which produced more FeSCN2+. With the increase in the concentration of the FeSCN2 positive ion, the rate of the reverse reaction increased. By the time it became equal to the rate of the forward reaction, the concentration of the FeSen2+ was still greater than it was before. We presume that the concentrations of the thiocyanate and the iron 3 ions had decreased. In the third tube, the concentration of thiocyanate ion was increased by adding solid potassium thiocyanate. This had the effect of increasing the rate of the forward reaction. Once again, when the rate of the reverse reaction caught up to that of the forward reaction, the concentration of the FeSen2+ was increased, the concentration of the thiocyanate was decreased somewhat, and the concentration of the iron 3 ion was lower than when it first started. In the fourth tube, the concentration of the iron 3 ion was reduced by precipitating it out with hydroxide ion. This had the effect of decreasing the rate of the forward reaction. By the time the rate of the reverse reaction had slowed to match that of the forward reaction, the concentration of the FeSen2+ had decreased, and the concentrations of the iron 3+ and the thiocyanate had increased somewhat. We can qualitatively predict the effect of changes in concentration on the system at equilibrium using LeChatelier's principle. This states that when a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce the change. In the first two cases, the concentration of one of the reactants was increased. This had the effect of shifting the position of the equilibrium to favor the product side, thereby reducing the concentration of the reactants. In the third case, the concentration of the iron ion was reduced. This shifted the equilibrium position to favor the reactants, so that the concentration of the iron was increased somewhat. Now we're going to examine this system to see if LeChatelier's principle accounts for changes in temperature as well as concentration. The reaction between the iron 3 and thiocyanate ions to form the thiocyanoiron complex ion is slightly exothermic. We write the equation with the energy term on the product side. This situation is not as easily explained because changing the temperature changes the rates of both forward and reverse reactions. However, if we examine the chemical energy diagram, we can see that at a given temperature, a smaller fraction of product ions possess sufficient energy to form reactants than the other way around. An increase in temperature should have a greater impact on the rate of the reverse reaction than on the rate of the forward reaction. Let's see if this prediction is borne out by experiment. The fifth tube is placed in a beaker of hot water. Note that the color fades as the concentration of FeSen2+ decreases. This tube is now compared to the first tube, and you can see that the color is indeed lighter. When this tube is placed in a beaker of cold water, the color darkens. So even though you shouldn't think of energy as a reactant or product, you can treat it as one or the other when you use LeChatelier's principle to make a prediction about the effect of a change in temperature.